In this first module, we're going to be looking at networking fundamentals. This is obviously the place to start. If you're getting into the networking world, if you're looking to get certifications, you have to understand some of the fundamentals. And the first fundamental that we're going to be going over is just an introduction to TCP/IP. TCP/IP is a protocol suite, but it's also a networking model. It's a collection of protocols that work together to allow communication on modern networks. TCP/IP is something that you are going to see and utilize every single day. And so we need to get into the fundamentals of that first. We'll also be looking at the fundamentals of Ethernet LANs. Ethernet is the primary LAN architecture that is used today. We'll look at wide area networks, which is connecting your local area network to other local area networks. Enterprises can have a large, centralized corporate offices and then many branch offices. Those would be considered wide area networks. Every host on a network is going to require an IP address, and still predominantly those are IPv4 addresses. So we'll go through IPv4 addressing and routing fundamentals, and then look at TCP/IP transport layer processes, as well as applications. Now, I do want to stress that we're going to spend a lot of time here, but these are still considered the fundamentals. And so in upcoming modules, we'll revisit some of these topics and go into them in more detail. So let's start just with a definition of computer networking. What is computer networking? And you may know this already or have heard some definition, but computer networking is simply the process of building connections between systems with a particular purpose, and that purpose is to share information, aka resources. The resources could be actual data that's being shared, a Word document, an Excel spreadsheet. The resources could be a web application that's used to input order details for a company. Resources could be physical hardware, like a printer. And so, but that's the purpose of the computer network, is just to connect systems together to be able to share those resources. The job of the network itself is to enable the movement of data from one place to another. We have two broad classifications for networks. The first is SOHO, small office, home office networks. And then the second would be enterprise. Now, clearly there's some gray area and some, medium-sized networks that that fall in between. You have a business that's got 45 employees but a single location. Well, is that considered a SOHO network? Probably not. Is it considered an enterprise network? No, probably not. So there's some gray area in between. But whether it's small or large, these networks are going to use similar technologies behind the scenes. Your understanding of the network is going to depend on your perspective. Okay? So in other words, the end user looks at the network just as a means by which they surf the internet, stream movies, use email. And then the network designer, the network engineer, looks at the network and sees all of the different moving parts, understands exactly how they work together, because it's necessary that you understand how it works together. The networking model is a fundamental component that serves as a blueprint or architecture for the network. It defines the components and the processes. It defines exactly how they work together. Networking models are very important. You don't build a house without a blueprint. And just the same, you don't build a network without some sort of plan. And so the networking model functions as that plan. Another name for networking models would be network architectures or network blueprints. Technically, this is a comprehensive set of documents that define the individual functions of the network. It defines individual components like the protocols. A protocol is a term that you're going to hear all the time. This is essentially a set of logical rules that define communication between two devices. Okay, so TCP is a protocol. IP is a protocol. Ethernet is a protocol. Rules that govern communication. Now, the extent to which they govern communication may not seem overly clear right away. It is very similar to, though, a language. In order for two systems to be able to communicate together, They have to be using a common language, just like in order for you to understand me, I have to be speaking a language that you understand. We can both speak multiple languages as long as we have one in common, and that's the way that network protocols are going to work. As long as we have protocol in common, then we can communicate that way. Now you've got physical requirements which would be included in the networking model as well. What's the wiring look like? What are the network devices that are going to be required for this particular network? Again, we're going back to the whole concept of a blueprint. Right? And then how are applications going to interact? All of these are components of the networking model. So rather than reinvent the wheel, we use networking models, and these are well-known networking models, in order to conform network devices and operating systems to a pre-built structure. It would not be a good idea, and historically this has been proven accurate, to allow individual manufacturers, individual developers to just come up with their own standards, okay? To say, well, I don't want to use TCP/IP, so I'm going to develop my own protocol and my own network devices. That wouldn't make any sense because you can't interoperate then with other networks. So the key is to use, pre-built, standardized networking models for your own network that you are building. And it's not even a question anymore. Everybody's going to do this. You don't even have to, it's become so standardized that you don't even have to worry about it. You have an operating system, it's going to support TCP/IP. When you purchase a network card or a switch or a router, they're all going to support and come pre-configured to a certain extent with the TCP/IP networking model. But the point here is just simply that model is standardized, it's well known, and there's a lot of benefit to using those things as opposed to reinventing the wheel. So today's world uses a single networking model, and it is known as TCP/IP. Now, you may have only heard about TCP/IP as a protocol, and that's accurate. It is a protocol. In fact, it's a suite of protocols that work together to help systems communicate over a network. But it is also a networking model. It defines, by very definition, it defines the communication on a network. It defines the functionality at the physical layer. It defines functionality for devices at upper layers. And we'll get into those layers here shortly. So everything has now standardized to TCP/IP, but it has not always been that simple. Originally, protocols and networking models didn't really exist. And so what I was just describing wouldn't be a good idea was actually the way that it was. Vendors would create their own proprietary offerings. And so IBM published a architecture known as Systems Network Architecture, SNA, in 1974, and that was used for many years. DEC and other vendors kind of followed suit, and the result of that was that systems from different vendors were not able to communicate with one another. You had to have products that would do translation between the two systems. Okay? And you even still dealt with that in the early 90s with systems like Novell and Windows, at least up at the application level, where they would have to have some intermediary device that was able to communicate with both sides and would translate. But it was even to that extent down at the networking level, which was even more cumbersome to deal with. So the fix for that was to get rid of these proprietary network models and to use open, vendor-neutral networking models. That would assist in competition. That's going to reduce the complexity of mixed networks as well. And so the International Organization for Standardization, or ISO, set out on a mission to do just that, to create that type of model. And they did this in the late 1970s. Now, the model that came to be from the ISO became known as the Open Systems Interconnection Reference Model, OSIRM, or just simply OSI. If you've done anything at this point with networking, you've at least heard reference to the OSI reference model. And if only for terminology, why do we don't want to get too far ahead here, but Why do we call a switch a layer 2 device? Well, because it functions at layer 2 of the OSI reference model. The same reason we call a router a layer 3 device, a hub a layer 1 device. So we use that kind of terminology, and it's in relation to this OSI reference model. Now, the goal of the ISO was to standardize network communications and data protocols and to provide global communication. In other words, come up with an open, vendor-neutral networking model that everyone can adhere to when they're developing devices, when they're developing protocols, when they're developing software. And if everybody's basing their offerings off of this standardized model, then that's going to open up global communication. Now, at the same time the ISO was doing this, the Department of Defense also started a similar effort. This was with the assistance of researchers, and they developed what is known as the TCP/IP networking model. This happened relatively about the same time, late 60s, early 70s. So we had these two competing networking models, and they actually weren't developed to be competitors to one another. They were just developed by two separate entities at the exact same time to address the exact same need, come up with a standardized model. Well, TCP/IP won. Okay, OSI is no longer a networking model that is utilized. TCP/IP dominates the world. You're not going to sit down at a computer and have OSI installed on it. But you will sit down at a computer, virtually every computer on the planet, and see TCP/IP installed. Whatever operating system, whatever type of device, it's utilizing TCP/IP. But OSI is still relevant. You might be wondering, well, why in the world are we talking about it? Is this just a history lesson? It is still relevant, and it's relevant due to terminology. And of course, TCP/IP is relevant in every single situation. The TCP/IP defines a large collection of protocols or a suite that allow computers to communicate with one another. Now, there are 6 core protocols in TCP/IP. You have TCP and UDP. You have IP, and then you have a few others that are a little less used. ICMP, ARP, ARP, and then the IGMP protocol. And I'm not defining those now because we'll get into those later. But those core protocols allow communication across the network. Then we also have application protocols. Application protocols will enable a program to interact with the network. So your web browser, for instance, is a program that needs to interact with the network. So it will use an application layer protocol, HTTP, or possibly HTTP with SSL, in order to interact and communicate across the network. Now, protocols, the rules that define communication, these are defined in a component known as an RFC, or request for comments. This is pretty technical documentation. If you go find one about a protocol, it will probably be far more than you ever wanted to know about said protocol. But they're a great source for information. They are really how the developers document the protocol itself, and so they are highly detailed. Other standards are referenced in TCP/IP to avoid repeating work. So for instance, TCP/IP is more concerned with communication between two systems, between applications. It doesn't really bother defining new standards at the physical layer, at the data link layer. Okay, it recognizes Ethernet, standardized by the IEEE as 802.3. It recognizes that as an official standard that's used on every local area network today. Okay, and so TCP/IP doesn't reinvent the wheel and come up with its own, lower level physical architecture. It just references Ethernet. It references several wide area network protocols as well, point-to-point protocol, frame relay, ATM, and others. Okay, so TCP/IP is the networking model that we're going to spend all our time on because it's the networking model that dominates today's networks. Now, a couple times so far, we've made reference to a layer, either in OSI or TCP/IP. Well, networking models use a layered approach to try to assist us, individuals, in understanding exactly what's happening. the layered approach really speaks to functionality that has to happen at a certain point. And so understanding the layer in which a device operates is going to tell me what that device is doing, or what it's capable of doing, or what it should be doing. Okay? So when we deal with applications or application layer protocols, things that interact with a particular application, then you're at the application layer. When you're dealing with protocols that are primarily responsible for end-to-end delivery of the data, aka transport, then you're looking at the transport layer. When we're looking at devices or protocols that are responsible primarily for routing and addressing, then we'd be looking at the internet layer. And then finally, when you're looking at something that's related to the physical architecture, actually getting data onto the network media, copper cabling or fiber, and sending it on its way, well, then that's the link layer. Okay? The original TCP/IP model was 4 layers: application, transport, internet, and link. The updated TCP/IP model, which is the one that would be used today, is 5 layers. And it's 5 layers just because it broke the link layer into 2. And we'll talk about that more in just a second. We also have a change in terminology. Okay, so the updated TCP/IP model is the application layer, the transport layer, the network layer, just name changed from internet, but still doing the same thing, addressing and routing, and then the link layer split into data link and physical. Okay. Now, when we say split, it's really just dividing the processes that were already at work in the link layer. It's a logical division. It's actually the division that the OSI reference model makes. Data link is concerned with packaging information to get it ready to go on the physical media. And physical is just worried about the electrical signals that need to be sent to send bits from one source to one destination. And so each individual hop, you have this communication that's happening. So 2 separate processes, and the updated model just broke it out into those logical processes.